So we've seen that we have this example for type node. Again, we're on EKS, not ECS. We have type node, and we looked at this. We have the metadata, and then we get the actual measurements. And we looked at some specific measurements. We looked at what node memory swap is, and what node memory RSS is, and what node memory reserved capacity. Well, we know what node memory reserved capacity is, and page fault and page major fault. What about this node FS? So one of the examples of a performance log event is for a node. One example is for a task. One is for a container. But one is for something called node FS. Can you explain what node FS is? Node FS refers to the file system FS metrics associated with a node in a Kubernetes or Amazon ECS environment. When monitoring containers, tasks, and node using tools like CloudWatch Container Insights, Node FS metrics specifically relate to the file system resources and usage on the node where the containers are running. I just wondered if it was a particular brand or something like that, a particular proprietary software, I don't know. So it just seems to be file, yeah, it's almost like a general term. So understanding Node FS in context, it's file system metrics. Node FS metrics provide insights into the file system performance and utilization on a specific node. And this includes metrics such as disk usage, I/O operations, read-write speeds, and the available disk space. These metrics are crucial for understanding how well the node's file system is performing and whether it is a potential bottleneck for applications running on that node. Here are some common Node FS metrics. We have Node FS underscore usage, the percentage of the file system that is currently in use. We have Node FS underscore used, the total amount of disk space that is being used. We have Node FS underscore available, the total amount of disk space available for use. Node FS reads, the number of read operations performed on the file system, and Node FS underscore writes, the number of write operations performed on the file system. What's the importance in containerized environments? Well, in containerized environments, monitoring Node FS metrics is important because containers may write logs, data, or configuration files to the underlying file system of the node. Insufficient disk space can lead to application failures or degraded performance. Understanding file system performance helps in diagnosing issues related to I/O operations, which can affect the overall performance of applications running in containers. And the fourth point relates to its integration with performance monitoring. Node FS metrics are integrated with other performance monitoring data, allowing you to correlate file system usage with other resource metrics like CPU, memory, and network usage. This holistic view is crucial for identifying performance issues and optimizing resource allocation. Okay, so it says Node FS auto-scaling group name as the first key, just like with the what was it, the pod? No, the node. Where did we have auto-scaling group name? It's the first thing. The node, yeah, auto-scaling group name. So we have the auto-scaling group name, then the CloudWatch metrics, and the value is an array. And CloudWatch metrics, meaning the metadata of the metrics, a specification of the metrics we're interested in. So node file system utilization, that's a great metric. And that's it. So for this object, but no, that is the only object we have, right? Open brace, closing brace. Then we have the dimensions, the node name, the instance ID, and the cluster name. But that seems to be it. It says cluster name, my CI cluster. CI, container insights, EBS volume ID, EBS, elastic block store, the operating system storage, not S3, it's not object storage, it's not the stuff that people use. Really, you don't tend to have a user interacting with EBS. AWS : //. You don't often see that. This is a schema. This part before the colon and the // is called the schema. US West 2B, that's an availability zone. /vol -0A53 and so on. So this, usually when we talk about IDs of resources, like an instance ID resource, it's this a few letters, then a dash, and then a series of letters and numbers. So I'm not sure if this whole thing is the EBS volume ID or just this bit, but anyway, instance ID, an instance type, node name, and then we get the actual measurements, the node file system available, node file system capacity. Any questions? Well, let's go through them first. Node file system inodes, node file system inodes free. Remember, index nodes, node file system usage, node file system utilization. Let's dig down in some of those, because we can read through them, but we don't really understand what's going on there. So for this example, PLE, which is the acronym I'm introducing for performance log event, the final keys are as follows. So we have node file system available, and they've put 1729.8395.136. Then we have a comma, and we go on to the next metric, which is node file system not available, but how much in the reserves. What's the node file system capacity? So node file system capacity 21462233.088, comma, onto the next metric, which is node file system inodes 1048.4720, and then node file system inodes free 1036.7158, and then the next key, node file system usage and that value is 4163.8379.52, and finally node file system utilization. Right, we're finished now, which is 19.400.754.794.0255. So what we know the units I was going to ask what are the units for one of the metrics, but the units we've only got the units for node file system utilization. Okay, so even though we've got these measurements down here, it doesn't mean we've got them all in this sort of metadata section in the CloudWatch metrics key. The only metric we've got in the CloudWatch metrics key is node file system utilization. Okay, but that's only one of these down here, node file system utilization. We've not said what the units are for node file system usage. Let's start with the first one though, node file system available. So what are the units for node file system available? Bytes. node file system capacity, again in bytes. Let's just get it sorted now. File system usage, bytes. File system utilization, that's Z. Utilization, anything that's a utilization is a percentage, so that's a percentage. And then inodes and inodes free, these metrics refer to the total number of inodes. So it's just a number. So inodes are the unit. So if it was 7, it would be 7 inodes. So it's not a specific measurement like bytes. And this is a good point. If you wanted to convert node file system available from bytes to a more human readable format, make that large sequence of digits more meaningful, you would divide the value by 1024 cubed. So we'd put 1024 cubed on the bottom here, and then get the result. So we had 17 billion bytes. That comes out to be about 16 gigabytes. So make of that what you will. I don't know how big, it depends how big the file system is. Early in the performance log event, there is a metrics key, CloudWatch metrics key, where we provide metadata. I've talked about this before with you. We provide a key called just metrics, and the value of this key is an array. But in this specific performance log event, the value of metrics is an array which only has one element. It is an associative array. The element is an associative array, and one of the keys within the array goes like this. So it's name, node file system utilization. My question is this: why might there only be one metric in this CloudWatch metrics key? In other words, why might there only be one metric which we provide metadata for? After all, at the end of the performance log event, we list 6 metrics. 1, 2, 3. We list 6 metrics, such as node file system available and node file system capacity. In certain scenarios, you may want to emphasize a specific metric for monitoring or alerting purposes. For example, you might be particularly interested in tracking the node file system utilization. Some performance log events might be generated at different levels of granularity. For instance, one event might focus on file system utilization, while others might cover a broader range of metrics. In this case, the PLE with a single metric can provide a detailed view without I don't think you understand. I don't think it understands. This is the performance log event. It includes all these 6, and I'm saying for only one of them we provide metadata. No, I'm not sure you understand. I wonder if we can get this as HTML, and then I'll be able to copy and paste it. So AWS CloudWatch documentation, and yes, each page of the documentation appears in Google searches independently. AWS CloudWatch documentation, container insights, node fs example performance log event. Here we go. Oh, no. Oh. No. There we go. There we go. Node fs. So put that back there. So here is the PLE. And my question is about why we only provide the units information for one of the metrics. Thank you for the clarification. Let's break down the reason why the CloudWatch metrics section only provides unit information for node file system utilization. Oh, okay, again, specific focus on a key metric. Okay, so the design choice to provide unit information only for node file system utilization might be intentional to highlight this specific metric as the primary focus of monitoring in this context. This metric is often critical for evaluating file system performance and capacity. By including unit information for only one metric, the PLE may aim to maintain clarity and simplicity, especially if the log event is intended to convey high-level information rather than an exhaustive list of all metrics with their units. It is common practice to assume or infer units for related metrics based on context. For example, metrics like node file system available and capacity and usage and inodes can be understood in terms of bytes or counts for inodes without explicitly stating their units. This reduces redundancy in logging while providing relevant information. Yeah, I don't really buy that. I'm asking why there's an inconsistency though. Why have we bothered to include the units for node file system utilization? The CloudWatch metrics section might primarily serve as metadata about the metrics being monitored rather than detailing every aspect of every metric. Yeah, this is what it looks like when CloudWatch doesn't really know the answer. When ChatGPT doesn't really know the answer. Since node file system utilization is often reported in percentages, its unit is emphasized. That doesn't make sense at all. Why would the fact that it is often reported in percentages mean that we want to emphasize the unit? No, it doesn't though. Okay. So let's just leave that for now. Type node disk IO. So we have an auto-scaling group name, EKS control my CI cluster node group standard workers node group, cluster name my CI cluster, EBS volume ID, and we have an ID for an EBS volume, instance ID, I dash such and such, instance type, node name, sources, CA, C advisor. I'm interested in that. So consider this PLE. Can you explain what C advisor is? And more generally, what is the sources section all about? in the context of your PLE, let's break down what CAdvisor is. CAdvisor is a shorthand for Container Advisor, and it's an open source tool developed by Google. CAdvisor that provides insights into the resource usage and performance characteristics of running containers. Here's a more detailed look at its features and functionality. CAdvisor collects and analyzes resource usage metrics for containers, including CPU, memory, disk I/O, and network usage. This helps users understand how their containers are performing in real time. It tracks the life cycle of containers, providing information on their status, their uptime, and resource consumption over time. This data is essential for optimizing performance and managing resources effectively. CAdvisor provides a web-based user interface where users can visualize performance metrics and resource usage, allowing for easier analysis and troubleshooting. CAdvisor can integrate with other monitoring and orchestration tools, such as Kubernetes, to provide a comprehensive view of containerized applications. When used with Kubernetes, it helps monitor container metrics in the context of pods and nodes. And there's Docker support. CAdvisor is specifically designed to work with Docker containers, making it a popular choice for organizations using Docker for containerization. So what's the sources section? Well, the sources section indicates the origin of the data, or metrics that are collected in the log event. The sources section helps identify which tool or mechanism generated the data being logged, and this is particularly useful in environments with multiple monitoring tools or sources of telemetry data. In your PLE, the source is listed as CAdvisor, Container Advisor. This indicates that the metrics included in the log event were collected by CAdvisor. This information helps users understand the context of the data and can assist in troubleshooting or further analysis. In scenarios where multiple monitoring tools are used, so we might have CAdvisor, Prometheus, CloudWatch, the sources section can contain multiple entries, providing a comprehensive view of where the data is coming from. So, back to the documentation. So yeah, we always have this sources section, and then it's an array for the value. Here it's just CAdvisor, one element CAdvisor. Timestamp using Unix time. No units, no uppercase T. Type node disk IO. Okay, so this is node disk IO. Now let's just take a moment to investigate IO. We are covering everything in this session. So the title. So one key goes like this. It has a value like this. Node disk IO. Sorry, type node disk IO. What is IO? Stands for input output. Okay, we all know that, but it refers to the operations that involve the transfer of data to and from a computer system or a device. In the context of node disk IO and your performance log event, here's a breakdown of what IO entails, meaning what it implies, what it has involved within it. There are types of IO. We have input operations and output operations. Input operations. These are operations that involve reading data into the system. For example, when a program reads data from a disk, it is performing an input operation. Words really matter. So it's reading, but we're describing the read as an input operation, which in a way is weird, but we are. Output operations. These involve writing data out of the system. For example, when a program saves data to a disk, it is performing an output operation. So you need to think of it not as going out from the disk. So it's not the case that we say when we take data from a disk, it's an output operation. Wrong. You should think of it from the perspective of the system. So when we say output, we primarily mean output from the system onto the disk. And so that's why we say when a program saves data to a disk, that's an output operation, because it's no longer in the system. It's as if the system can almost relax now, like when a human being can relax because they don't have to keep memorizing something because they've just written it down on a notepad with a pen. They've outputted it to the notepad. So an output operation is when a program saves data to a disk. Disk I/O. This term. Disk I/O specifically refers to the read and write operations performed on a storage device, such as a hard disk drive, a solid-state drive, or any other type of storage. So what's the importance of disk I/O? Monitoring disk I/O is crucial for understanding the performance of applications and the overall system. High I/O wait times can indicate that the disk is a bottleneck for performance. In a containerized environment, managing disk I/O is vital for ensuring that applications run smoothly, particularly when they are I/O intensive. Tracking I/O operations helps maintain data integrity by ensuring that data is read and written correctly and efficiently. So an input operation is simply a read. Yes, exactly. In the context of I/O operations, an input operation is essentially, roughly, a read operation. Input operations involve transferring data from an external source into the computer or application. This could be data being read from storage, input devices, or network sources. When a program reads a file from a disk, it is performing an input operation. When data is received from a network socket, e.g. downloading a file, that also counts as an input operation. Retrieving records from a database, or pulling data from an external API, that's an input operation. To contrast this, output operations involve writing or sending data out of the computer or application. This includes saving files to disk, but also sending data over a network or displaying data on a screen. Okay. So we have node disk I/O, I/O service bytes async. What's that? What's that all about? So there is a performance log event for node disk I/O. Node disk I/O. One of the keys is node underscore disk I/O underscore I/O underscore service underscore bytes underscore async. What is this all about? It's a metric, and it provides information about the amount of data in bytes that has been transferred asynchronously via I/O operations on a disk. So, node. Part of the metric name is node. This indicates that the metric is relevant to the node, the physical or virtual machine within your container or orchestration platform. And then it says disk I/O, like that. It's all written lowercase, no spaces, disk-io. Well, this refers to input-output operations related to disk storage. And then it says I/O service. This part indicates that the metric is capturing data about I/O operations being serviced by the disk. It says bytes in the name. This indicates that the measurement is in bytes. It says async. This specifies that the operations being measured are asynchronous. In asynchronous I/O operations, the I/O request is initiated, and the application can continue executing without waiting for the operation to complete. This is so in a way it queues it up. So it asynchronously does it. It doesn't do it in real time. It says it's as if the application goes, okay, get on with that disk, and the disk does it when it's ready. This is typically done to improve performance and responsiveness. So asynchronous operations we're talking about. In modern computing environments, especially in cloud or distributed systems, asynchronous I/O is frequently used. It allows for non-blocking operations, enabling applications to handle multiple requests simultaneously without being stalled by slower I/O operations. By tracking metrics like node, disk I/O, I/O service, bytes, async, administrators can gain insights into how much data is being read or written asynchronously. This information is valuable for assessing disk performance, identifying bottlenecks, and optimizing the application behavior. I have another question about I/O. Do people ever measure I/O in relation to random access memory? Why is this for disk storage? Does it have to be disk storage, or is it storage generally? So I said, do people ever measure it in relation to RAM? Yes, I/O measurements can also relate to RAM, particularly in the context of memory management. No, I said oh, okay, no, we can't, yeah. RAM is a type of memory, and when data is read from or written to RAM, it can be measured in terms of I/O operations. For instance, when an application accesses data in RAM, these access operations can be considered I/O operations, albeit in a different context than disk I/O. The performance of RAM I/O operations can be critical for application performance, since RAM access times are significantly faster than disk access times. When a system runs out of available RAM, it may use disk space as a temporary store for data that would otherwise reside in RAM. This process is known as paging or swapping. And in this case, page I/O is a term that refers to the read and write operations between RAM and disk. When data is moved from RAM to disk, or from disk to RAM, swapped in, it involves I/O operations. Monitoring I/O, or the I/O related to paging, can help identify memory pressure situations and performance bottlenecks. Cache I/O. RAM is often used as a cache for faster access to frequently used data. Measuring the I/O of cache hits and misses, that's when data is found in the cache versus when it has to be retrieved from slower storage. So measuring the I/O of cache hits and misses can provide insights into the overall system efficiency. So we have node disk I/O service bytes async, node disk I/O service. So it's all the same beginning. Node disk I/O service bytes, node disk I/O service bytes, node disk I/O service bytes. But we have async, read, sync, total, write, async, and then we move on to serviced. So we have service, 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 serviced. Serviced, serviced. That's a good question then. What is the difference between the metric node disk IO service bytes async and node disk IO oh no, it's disk IO node disk IO underscore IO and node disk IO serviced async. So first of all, service. I'll just go to the... So service measures the amount of data transferred, while serviced counts the number of I/O requests. So the former, service, provides insight into the volume of data being processed asynchronously, while the latter is how many asynchronous operations are completed, offering a sense of I/O operation frequency. So if we look at the actual values, let's focus on async for now. So we have async and async. So for the service one, it's 9,750. But for the service one, for the serviced, it's 1.15. So we've gone from 9,000 to 1.15. And we're being told that serviced is to do with the number of operations. So we've got just over one operation. Is that right? But this is in bytes the number of the amount of data being transferred. Okay, fine. And just to look at again the other parts of this PLE, we have an auto-scaling group name, we have a cluster name. We have an EBS volume ID, which is written almost like a URL. We have an instance ID, I-. We have an instance type, t3.extralarge, node name, and notice the structure of the node name. The reason this is an IP address, 192.020, the reason we have to use dashes for the IP address is because dots are already taken as a delimiter. We use a dot to delimit the IP address from the region, from the word compute, from the word internal. So we have to use dashes for this. So we do IP-192. So there are 4 parts to the node name. We have an array for sources. We have a timestamp using Unix epoch time. And it's in milliseconds, and that's 1. So it's 1. So it's 928,096,567,000,000,000, 1 trillion. Type node disk IO, version, and then a string for the version. Even for this node, the node disk IO, we give it a version, right? Version, and we have this device key, and the value is /dev NVMe 0N1. Then the next performance log event is node net. The next example performance log event is not for disk IO, but it is instead entitled node net. What is this? Is this just node network? The node net metric refers to network related. It's not actually a metric, by the way. It's not the name of a CloudWatch metric, but okay, we'll allow it. The node net refers to network related performance metrics, and it is commonly used in environments like Kubernetes to monitor the networking aspects of nodes, which are crucial for understanding network performance and diagnosing network related issues. So node net, all one word. The node net metrics are designed to provide insights into the network traffic being handled by a node. This includes both incoming and outgoing network data, which can help identify bottlenecks or performance issues in network communication. again, I was just checking it's not a brand, some sort of proprietary software. I believe it's probably it probably is a kind of specific name. It's obviously stylized in a quite unique way, but it's a kind of Kubernetes feature or something like that. Kubernetes API, I don't know. So we have an auto-scaling group name, and it's got 5, 6, 7 different segments for the auto-scaling group name. Cluster name, my cluster, instance ID, instance type, t3.large, and then a node name. Think about it. It's got 4 parts, .compute, .internal. Think about that for a node name. Sources, this time we've got 2 sources, cAdvisor and calculated. That's one of the sources. So what does that mean? And I believe we're going to... maybe they go into that later? I don't know. Timestamp. And we have 1, 2, 3, how many digits? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 digits. Type NodeNet. Version 0. Interface. ENI stands for Elastic Network Interface, which is the actual essence of anything that interacts with the network on AWS. So really, I was going to say it's the essence of an EC2 instance, but I think technically an EC2 instance can have multiple ENIs. So Elastic Network Interface. But you can see how we might want to have an interface key if we're talking about things related to networking. So we have interface, we have Kubernetes, and the Kubernetes value is just an object where we specify host. And you can see that the host name, well, we recognize this structure, a hyphenated IP address, .compute, .internal at the end is very similar to the node name. It's just a way of giving the name of a host, the name of a node. The host is the node in this case. Not all hosts are nodes, but in this case the host is a node, and that's why it's the same name. 020.192.0.20.19. Oh no, it's not the same name. Okay. So I was wrong. But the structure of the name is the same. And now onto the metrics. We have node interface network received bytes, node interface network RX dropped, node interface network received errors, node interface network received packets, node interface network total bytes, node interface network transmitted bytes, node interface, and interface here presumably means elastic. Does that mean elastic network interface? We're using Elastic Kubernetes Service. I know, and it's an Amazonian construct, the ENI. But maybe there is such a thing, a distinct thing as a node interface. Let's have a look. So the metrics in this PLE include node interface network RX dropped, meaning RX meaning received, network interface network RX errors, and so on. Does the interface in the name of these metrics refer to an elastic network interface? Or is there such a distinct thing as a node interface in Kubernetes, for example? The term interface typically refers to a network interface on the node which can include, yes, an elastic network interface, which is virtual, it's not a physical thing, and it is the thing that provides the instance with its own private IP address and its public IP address and the set of security groups. Yes, that's a key point as well. The thing that the security group protects is actually the ENI. ENIs are often used in cloud environments like AWS to manage network traffic for instances, but the interface could also be referring to a physical or virtual network interface. Notice the absence of the word elastic. So in Kubernetes, the term interface can refer to the underlying network interfaces on the host machine, e.g. ETH0, ETH1. These interfaces are responsible for handling network traffic to and from the pods running on the node. So maybe that's the answer. Maybe. So we have 1, 2, 3, 4 received. One of them is just total bytes. And then we have 1, 2, 3, 4 metrics related to transmitting bytes. Next, a pod. PLE. Lots of metadata here. So one object with the unit percent for pod CPU utilization. Unit percent for pod memory utilization. Bytes per second. Remember, it's tied to the time unit, this received bytes. Pod network TX bytes, transmitted bytes, and so on and so on. And this time we've got a dimensions array, but look, it's got one element, or a 0if element, a first element, a second element. What's going on there? So let's investigate this. Please, without commenting yet, take a look at this PLE. I'm about to pose a question to you. Okay, this is my question. The dimensions key seems to have an array as its value, where the array has many elements. Okay. So we have, this is it. So dimensions, and then opening square bracket, and then we've got 0if, 1. Let's just copy that. So we've got 1, 2, 3, 4 elements, ending in the third element, because we use zero-based counting. How does this work? I know that an array is an ordered list. So is it the case that the 0if dimension, the 0if element in the array specifies the dimensions for the 0if metric? And the first element in the array for the first metric, etc. Is that it? Is that the case? Because if it is the case, it doesn't look to be the case, because we do have an array for the metrics key, an ordered list, opening square bracket, closing square bracket, but we've got 3, 4, 5, 6 elements here. So we don't actually have 4 elements here. So it can't be the case that this is directly corresponding to this array here, because in this array, the dimensions array, we've got 1, 2, 3, 4, but we haven't got 1, 2, 3, 4 metrics. We've got 5 and 6. So it can't be the case that for pod CPU utilization, we're interested in these dimensions, and for pod memory utilization, we're interested in these dimensions. That doesn't work, because we've only got 4 elements in the dimensions array. So what's your response? In the context of the performance log event you provided, the dimensions key is indeed an array of arrays, where each inner array does define a set of dimensions that can be associated with metrics. But here's how it works. Each inner array specifies a different set of dimensions we know that can be used as a filter or category. The dimensions are used to uniquely identify the metric data points. The dimensions do not have a direct one-to-one mapping with the metrics listed in the metrics key. Instead, they provide additional context that can be applied to the metrics. For example, in your provided dimensions, the first inner array, which is pod name, the namespace, and the cluster name, that dimension set may correspond to metrics like pod CPU utilization or pod memory utilization, giving you insight into CPU and memory usage for a specific pod within a specific namespace and a specific cluster. I don't think you've quite answered my question. How do they map up with each other? Well, I think it's just the case that each metric can have any of the dimensions. I mean, ChatGPT says not exactly that. It says each metric can have a different set of dimensions. The structure is designed for flexibility rather than a strict one-to-one mapping. Each inner array in the dimensions key corresponds to a category of metrics that may share similar dimensions. However, there is no guaranteed one-to-one mapping based on index alone. Each metric in the metrics array can use one or more of the dimension sets defined in the dimensions array to filter or categorize the metric data. For example, you might see metrics for CPU utilization or memory usage that would use this pod name, namespace, cluster name set to provide specific context about which pod's metrics you're looking at. So here's an example for clarity, assuming the following mappings. So we have, these are our metrics: pod CPU utilization, memory utilization, network received, and network transmitted. And we have these 4 dimension sets: pod name, namespace, and a cluster name, service namespace and a cluster name, a namespace and a cluster name, so no comment about the pod, and just a cluster name. Here are the possible mappings. That first metric, CPU utilization, might use the first set of dimensions, pod name, namespace, cluster name, to give CPU usage data for each pod in a specific namespace and a specific cluster. But pod memory utilization could also use that first set of dimensions. Pod network received bytes could use the second set, services namespace, cluster name, to provide network metrics for a specific service in a namespace and cluster. Other metrics might utilize the remaining sets of dimensions based on their relevance. So why is an array used? Why is the data structure of choice for conveying this information an ordered list? Well, it has several advantages. Arrays maintain the order of elements, which allows for easy access to specific dimension sets. If you know the index, like is it first, second, of a dimension set, then you can quickly retrieve it without needing to search for a more complex data structure. Different metrics may require different combinations of dimensions. An array allows you to easily list out these combinations without rigid constraints, making it simpler to manage various metrics that might require different dimensions. An array can easily grow or shrink in size. If you need to add or remove dimension sets as your metrics evolve, e.g. introducing new metrics that require different dimensions, you can do so without much overhead. This adaptability is particularly useful in dynamic environments like Kubernetes. And the use of an array of arrays allows for nested organization. For example, you can have a first level that groups metrics by their relevant dimensions, and a second level that specifies the actual dimension names. This hierarchical structure makes it easier to manage related groups of metrics. I'm not sure I understand that. I know what they mean by a nest, one thing within another, but I don't know. And also it helps with iteration. Arrays are easy to iterate over, which is beneficial when processing metrics and dimensions programmatically. Okay, fair enough. So that's how it works. We have an array of arrays for the dimensions key, but we do not have the unit and the name of a particular metric. Obviously, they are just a bunch of properties. You could have unit first, then the name first, then the unit, and so we don't use an array for that. But overall, each metric, this metric, then this metric, this ordering is this is an order. This list is an ordered list as opposed to an unordered list. So there is an outer array, but for the metrics key, there's not an inner array. This is not an array, right? These are curly brackets. So this is an unordered list here. Timestamp, type pod, version 0, Kubernetes. We just have a Kubernetes key which lists a host, which has a host, and then labels app :CloudWatch agent statsd, pod template hash, and then a value for that. Namespace, name, Amazon CloudWatch, pod ID, and it's this kind of thing separated by dashes. Service name, CloudWatch agent statsd. And we have lots of different metrics here. Some relating to CPU, several relating to pod memory, and several relating to the pod network, and the pod number of container restarts, and so on. So that is, I think we got lost there. So we have type pod, type podnet, and type container fs, type cluster service, type cluster namespace, and next time we'll just begin with relevant fields in performance log events for EKS and Kubernetes.